In this video, I will explain you about biasing of PN junction diode. So as a subtopic, we will cover forward biasing, reverse biasing and characteristics of PN junction diode under forward and reverse biasing, and also we will cover dynamic resistance. Now these concepts are connected with each other, so that whenever you are watching this lecture, do it completely. Okay, because this is a very important portion for your board examination, and in semiconductor this portion makes 60% of the total syllabus or syllabus from chapter semiconductor. Okay, now we will see what is biasing. Biasing is simply providing potential difference across PN junction diode. Now in a PN junction diode, we have two polarity, or I can say that we have two types at each end. This one is P type, this one is N type. Now in the case of a conductor, it's the same type. Here also it's the same thing, here also it's the same thing. See, if it is a copper conductor, if you are cutting the conductor into n number of small pieces, every part would be equal to each other in terms of property, property like conductivity, resistivity, number of electrons per unit volume, all these would be similar to each other. But here it is not in that way. One end is P type and other end is N type. Now this can be provided with a potential difference in two ways. One is with P connecting positive terminal of the battery and with N connecting negative terminal of the battery. This is one type, and the second type is with PN junction. This is a diode. Okay, so we will call it as diode. This one is a PN junction diode. Okay, we have P type at one end and N type semiconductor at other end. Okay, now this can be with P I can connect negative terminal of the battery, and with N I can connect positive terminal of the battery. This is one type and this is next type. This is called as forward biasing. Forward biasing, and this one is reverse biasing. What is the difference? Here with P I have connected positive terminal of the battery, and here with P I have connected negative terminal of the battery. So P with positive, N with negative, forward biasing. P with negative, N with positive, reverse biasing. Okay, so these two topics comes under biasing, that is providing a potential difference or connecting a cell across a PN junction diode. Now we will see what will happen when a PN junction diode is forward biased. So as I have explained, it is simply connecting the P type with positive terminal of the battery and N type with negative terminal of the battery. Now first we will ignore the fact that the cell is connected here. How this depletion layer is formed? Previously we were having holes here, right? Because this is P type semiconductor, majority charge carriers are holes here and minority charge carriers are electron here. And the N type semiconductor was having electrons here, and because electrons are majority carriers in the case of N type semiconductor, and holes are minority carriers, but these holes are attracted by the electron, or I can say the electrons are attracted by holes, so both will move towards the junction and they will recombine. Okay, so they will diffuse together, so that after diffusion there will neither be electron nor be holes. Okay, now what will happen? This would be an area where charges are not present or charge carriers are not present. Okay, that makes significance here. Charges would be there with the silicon atoms, electrons would be there, protons would be there, but charge carriers are absent because these carriers diffused or combined, making no charge carriers. So these are the region of depletion, or these are depletion region. Okay, now as this lost electrons, this will become positive charged, and as this lost holes, this will become negative charged. Now across this we have an electric field from positive to negative. Now this electric field is applied across a distance of d, that is the thickness of depletion region, right, depleted region. We have learned potential difference is equal to E into D, which means now this is associated with the potential difference. Higher the D, the thickness, more will be the potential difference across this in this direction. Okay, so if the depletion layer is more, then the barrier potential would be more. Why we are calling it as barrier potential? Now once the depletion layer is formed, then it stops the further diffusion takes place. Why? Now the holes cannot go and combine with the electron because this electric field, see, electric field is in this direction, so it doesn't allow the positive charged hole to go in this direction, and that doesn't allow electrons, negative charged electron, to go in this direction. See, this is the direction of electric field, right? If I am keeping a positive charge here, then positive charge has a tendency to move in this direction. Okay, but at the same time, see, one thing is very important. There would be current due to minority charge carriers. Here we have lesser number of holes, right? With n-type, the minority charge carriers are hole. Now with p-type, minority charge carriers are electron. Now these holes can easily come to the junction, and from this junction it will go to this direction, and even electron, minority charge carrier here, can go to this direction, and this electron would be brought to the junction. So hole electron combination is possible here, or diffusion is possible here, but that is a very small amount of current, or I can say it as it's a current created due to minority charge carriers. So we can ignore about this effect due to minority charge carriers because they are very less in number, but as an additional information I have told. But anyway, here at this position, current due to majority charge carriers are 0 because now combination is not possible. So we have positive charge here and negative charge here, and creating a barrier across this that stops the process of diffusion or combination. Now here we are connecting a cell in forward bias, which means positive terminal with p-type and negative terminal with n-type. What will happen? See how it is supposed to send current. If at all, if it is sending current, if this Pn junction diode is permitted for the conduction, I could say that from here positive charges will come, or I can say this positive terminal of the battery will push the holes in this direction, and the holes will cross the barrier potential, and the holes will go here, and that will recombine with an electron. Now when an electron is lost from here, it will send one more electron here. When a hole is lost from here, it will create a hole here. Again the hole will be pushed to here, and it will recombine with electron. Again current is made. See, from positive terminal, this positive terminal will push a hole in this direction, and the hole will come here, that will diffuse with an electron. Now we have an electron less here, that electron will be supplied by the negative terminal of the battery. Now it is restored back. This will also give a holes, this will also create a new hole, and this hole will again go to this direction, or it is only with one holes and electron, and the same type of process will happen with other holes and other electron, which means there would be a continuous flow of current across this thing. So this will happen only if this allow charges to conduct, but there is a problem here. These holes cannot simply jump across this, because if the holes come here, let's say the positive charged hole, if it come here, it is offered by a repulsive force by barrier potential, because barrier potential is in this direction. We have a depletion layer here. So first what it has to do, this EMF should be such a value so that this can overcome the barrier potential. Okay, now if the barrier potential is 0.747 volt, say for example, if I am giving 0.1 volt, will there be a current? No, because 0.1 volt, when we are applying across 0.7 volt, this is not enough to overcome this. But what will happen, you know, now the potential difference across this is 0.7 when the EMF is not connected. Now when 0.1 is connected, this width will decrease. Now it will become, so from here, this is the initial thickness, right? So I am applying 3 potential differences, 0.1, 0.2, then 0.4, then 0.7, then 1 volt. Okay, so after applying, next scenario, when I am applying 0.2 volt here, this 0.2 volt would push this border a little bit forward, because this is able to do some work, but this is not able to, you know, overcome the barrier potential. So initially this was 0.7 volt. Now after applying 0.2 volt, the thickness of barrier potential would be, or depletion region would decrease. Now that would become this less. Initially it was this, the thickness of depletion region. Now this will become this. Now again I am applying a 0.4 volt. Where I am applying here external potential, I am making it 0.4 volt. What will happen? Again the depletion region will decrease. The width of the depletion region will decrease. Now I am applying 0.7. What will happen? This 0.7 would be able to completely oppose the barrier potential, so that now the thickness of the depletion region would be a line. See, this is the barrier potential initially. Now on applying on increasing potential, see, it has become a lesser value. Now to send current, it has to only oppose this much barrier potential. Now we have again increased the external potential. That has reduced the thickness of depletion region. Now the value is this much. Now to send current, we are very close towards conduction, because now we have to increase the value in such a way that our external potential will be equal to the barrier potential. So I have kept 0.7 volt, and now this 0.7 volt of external potential is able to completely oppose the barrier potential, and any value higher than this would be conduction of current. Can I plot that on a graph? I am applying a voltage here, and this is the current, and here it's a forward bias, because see, I am applying V positive. So this is forward bias, this one is reverse bias, because my potential difference is here positive and here negative, right? So from 0 I am increasing the potential. I have applied 0, there is no current. I have increased the external voltage to 0.2 volt, but what it has done, it has decreased the thickness of depletion region, but there is no current, 0.2 volt. With 0.4 volt, again the barrier potential is 0.7, so 0.4 is not enough to overcome 0.7, so overcome the opposition offered by 0.7, no current is still the 0. 0.7, at 0.7 is also current is 0, but after 0.7 the current started increasing. So I can say this would be the graph. Now 0.9, 0.8, 1 volt, 2 volt, 3 volt, whatever the value we are giving as external potential which is above the barrier potential, it would be sending current across. Now holes can move across this PN junction. They would combine with electron, and that electron would be supplied by the negative terminal of the battery, making a closed circuit. Very clear? The next thing is a reverse bias. Reverse bias is very simple. Here what we are going to do, we are going to just connect the N type with positive terminal and P type with negative terminal. What would happen in this case when I am offering 0.2 volt, 0.4 volt and 0.7 volt? Now see, this negative terminal would attract these holes in this direction, right? So this negative terminal will try to get these holes. So this depletion region, this border will move to this side, and at the same time this positive terminal would try or would give a potential such a way that it needs the electron from the N type, which means that this border will move outward. What will happen? See, here the depletion region was, the thickness of the depletion region was reducing, but when I am applying 0.2 volt here, initially this is the thickness of the depletion region. Now that will increase to a next value. So higher the depletion region, higher the thickness of the depletion region, higher would be the resistance, because depletion region offers opposition for the movement of current or movement of charges. Okay, now I am increasing the value to 0.4 volt. What will happen? Again from here that would increase. See, can you see one thing? 0.7 volt, the depletion region will now increase. See, this is P type, this is N type, P type, N type, P type, N type. Can you see one fact here? See, the resistance of PN junction diode is increasing, or barrier potential is increasing. See, how barrier potential will increase? We know that E into D would be barrier potential. As this thickness increases, the barrier potential will also increase. So this will not send current, this will never send current, because the resistance is being increased. See, it can only send current if the barrier potential come to 0, or if the depletion region, if it is made to a value having thickness is equal to 0, and if it can send charges across the barrier, across the PN junction. Okay, but in the case of reverse bias it is never possible, because the resistance that keeps on increasing. But there is one very important thing. What will happen when I am applying a negative potential here? See, it's a positive or a reverse potential here. See, sorry, with N we are connecting positive, with P we are connecting negative. Now with N, majority charge carriers are holes, but there are minority charge carrier electrons. Sorry, with N the majority charge carriers are electron, and this is majority, and minority charge carriers are hole. Now with P, majority charge carriers are holes and minority charge carriers are electron, and depletion region here it is positive, here it is negative. Now see, these minority charge carriers, this positive would be pushing the minority charge carriers. Here it is holes. Now this holes, if it jump here, now again the barrier potential will push the holes along in this direction, because see, this is the electric field offered by barrier potential. Now this holes can easily come here. It will happen with the same will happen with electrons. The negative terminal of the battery is pushing holes here. Now electron here, negative repulsion, so the electron will come to the depletion region, and in depletion region if an electron come here, this negative charge in this side of the depletion region will push the electron in this direction, so that electron hole combination will happen, making a current. So this process will keep on be continuing. But see, the number of minority charge carriers, as the name suggests, it is very less. So this current due to minority charge carriers are very less. So generally we say with perspective of majority charge carriers. Here in reverse bias, I would say current is 0 in reverse bias, because I am only talking about majority charge carriers. Majority charge carriers cannot form any current or cannot make any current in reverse bias, but minority charge carriers would be there. So this is measured in milliampere. Now if I am drawing this in milliampere, then I can never find a current here, but I am going to take the scale of this reverse bias in microampere, so that I would be able to plot a small amount of current. So here what will happen, this current would be almost same. It's a small amount of current. Don't compare this with this. This is made with milliampere, this is made with microampere. But if you are increasing the reverse biasing beyond a limit, what will happen? This potential would be such a high value so that it can make more electron hole pairs. Now if more number of electron hole pairs are generated, see, when it is intrinsic semiconductor, there is nothing called as majority charge carriers and minority charge carriers. See, with the silicon crystal, a pure silicon crystal, see, it's bonded in this way. Now whenever one electron is generated, whenever it gives out one electron, a hole would be generated here. Whenever this gives out one electron, a hole would be generated. So in an intrinsic manner, or when it is thermally generating free electron, equal to that number we will have holes. But P type and N type, these are having additional holes and additional electron, because it is doped with, here in this case, trivalent atoms, and this is pentavalent atom. That is the reason for excess charge carriers here, or that is the reason for majority charge carrier here. Here holes and here electron. But when we are creating electron hole pairs, either it is thermally, or here in this case, when I am increasing the reverse potential beyond a limit, this potential would be such a high value so that this would be able to take an electron from its lattice point. So whatever the number of electrons are generated, equal to that number we will have holes. What I am saying is, if 100 electrons are taken out from the covalent bond with higher potential, equal to that number, that is 100 holes would be generated in the semiconductor. Okay, so what will happen? Higher the potential, reverse potential beyond a limit, what will happen? Breakdown will happen. In that case, more electron hole pairs would be generated. Whatever the number of electron generated, equal to that number of holes would be generated, and making a lot of minority charge carriers, and this will contribute towards higher current, or I can say that from there onwards current would be exponentially increasing. So this is called as breakdown. And what is the reason? Generation of electron hole pair with higher reverse potential. Okay, reverse bias with the potential, higher potential applied across in reverse biasing. Okay, so this is forward biasing, this is reverse biasing, and here it is microampere. The small current is due to minority charge carriers. This is due to breakdown, that is exponentially generated electron hole pairs with higher potential difference. Here till this voltage, this is called as knee voltage or cut-in voltage, because in forward bias at all the stage there are no current. Till the knee voltage, till the cut-in voltage, there is no current, because till then it is giving a position for the barrier potential. Whenever our external potential is equal to the barrier potential, from there onwards we will have current in the circuit. So knee voltage is very important. This can also be asked as cut-in voltage, and this is forward bias. And see, from here we can see V is directly proportional I almost. So we would be able to get the value of resistance, and the resistance is not constant here. See, the slope is different at different point of the graph. So we will calculate dynamic resistance. So at this point, in between these 2 points, if you want to get the resistance, we would take the x projection and y projection. So this is delta I. See, this one is initial I1 and this is I2, and this one is delta V. This value is V2 and this value is I2. So this is V2, this is V1, this is I1 and this is I2. Now resistance is equal to V by I. So delta V by delta I, delta V by delta I would be the dynamic resistance here, R dynamic. That is not the slope. Slope is delta I by, see, y by x is the slope. So I can say R dynamic in this graph is the inverse 1 by slope, or 1 by tan theta, or this is cot theta. Because slope is always opposite by adjacent. Here we are taking adjacent by opposite, okay, which is cot theta. So this concept you should be very clear with. What is forward bias, what is reverse bias, and why current is moving in forward bias, why current is not going in reverse bias, characteristics of PN junction and dynamic resistance. Now, how to represent the whole scenario in a PN junction diode. So always it is very difficult to draw PN junction diode in this way. Now onwards I would represent a diode in this way, and this is an arrow, right? So this is the direction of movement of charges, positive charges. Always we will take positive charges as the standard, right? Now always current will move from positive to negative. So this is the PN junction diode. Now if I am connecting a positive terminal of the battery here and negative terminal of the battery, current would go in this direction. Now at the same time with the PN junction, so this is P and this is N. With the PN junction, if I am connecting a positive terminal here and negative terminal here, see, this would say that stop the current. Okay, now this is forward bias. In forward bias, current would be there, current due to majority charge carriers is present, or I can say that when a PN junction is connected across DC, it would send current only if it is forward biased. When it is reverse biased, there is no current. Okay, so current would go in this direction. See, it says stop. Here it moves in this direction. Okay, so always it is from positive to negative. That is the meaning of this arrow, this triangle. And in forward bias, conduction would be there. In reverse bias, conduction is 0. Forward bias, lesser resistance. Reverse bias, very high resistance. High resistance means it would behave as insulator. So reverse bias is equivalent to insulator. And forward bias is equivalent to conductor. This is a very important concept. Okay, thank you.